Welcome to this eLearn security video training lesson on exploiting buffer overflows. In this video, we will see how to exploit a buffer overflow in an FTP client application. Although this is a very old application, it will be easier for you to understand the entire exploitation process. Moreover, please consider that the steps we're going to see can be used in newer software and tools. We already know that the application is vulnerable to buffer overflow. When the application connects to an FTP server and receives the banner, if the banner is too long, the application crashes. In order to exploit the vulnerability, we will create a small Python script that will act as an FTP server. The script will serve the banner with our payload. Let us inspect the code of our fake FTP server. It is a simple script that we will edit during the video. The payload variable will contain the banner to send to the FTP client. This will trigger the buffer overflow. It will be composed as follows. First, we add the junk bytes needed to reach the EIP. Then, we will append the address that will overwrite the EIP. At the end, we will add our shellcode. This is the code that we want to execute on the target machine if the buffer overflow works. The rest of the code creates a listener on port 21. Once the client connects to the listener, it replies with a 220 code, followed by our payload. The first step is to identify how many bytes we have to send in order to trigger the buffer overflow. To do this, let us open Immunity Debugger and load the vulnerable client application. Let us use Mona to generate the payload to find the correct number of bytes. We can do it with the following command. PC stands for pattern create. 1200 is the number of bytes that we want Mona to create. Let us run the command and see what we get. As we can see in the logs, Mona creates a file named pattern.txt, which contains the pattern to send to the vulnerable application. Let us open the file and copy it. The plugin creates a different version of the payload. We are interested in the second. Therefore, we will copy and paste it in our Python script. Thanks to this payload, it will be very easy to find the correct amount of junk bytes to use in order to reach the EIP. Let us save the script and run it from the command prompt. Right now, the server is listening and waiting for the connections. As soon as the client establishes the connection, the script will serve the payload that we have just added. So let us go back into Immunity and run the client application. Since it's a non-licensed version, we will have to wait a few seconds before it starts. In the first window, we have to set the address of the FTP server. Since it runs on the same machine, we can use the local host address and click on Connect. If we go back to our FTP server, we can see that the connection has been established. After a few seconds, we can also see that something happened in Immunity Debugger. Indeed, it seems that the application crashed. We can see that the stack is filled with our payload and that the EIP register contains part of it. This value will help us to detect how many junk bytes to use before reaching the EIP. To do so, let us run the PO command, followed by the value contained in the EIP register. PO stands for pattern offset. The only purpose of the command is to return the number of bytes used in the payload before overwriting the EIP. As we can see in the results, it seems that the value is 989 bytes. Therefore, we know that we need 989 bytes before actually overwriting the EIP. So let us go back to our script and edit it accordingly. Let us delete the payload just used and instruct Python to generate this hexadecimal value 989 times. Let us now append the following 4 bytes to the payload. This will help us check if the amount is correct. If so, the EIP will contain this hexadecimal value, which is the hexadecimal representation of 4 capital A characters. Let us save the script and reload both the server and the client. Let's establish the connection with the server once again and wait until the application crashes. Here we go. We can see we have successfully overwritten the EIP with our value. Therefore, the amount of the junk bytes is correct. Of course, the application crashes. This happens because the client tries to jump the address location pointed by EIP. What we need now is the address of an instruction such as call ESP or jump ESP. As we can see in immunity, once the return instructions get executed, ESP points to the memory address right after the overwritten EIP. Therefore, if we add the address of a call or jump ESP, the program will continue the execution and will start executing whatever is at this position. As you can imagine, this is the position where we're going to insert our shellcode. Here we will insert the instructions that we want to execute. We can do this by simply appending the shellcode to the previous payload. Our current payload ends here, but if we add more data, it will be copied in the following position on the stack. Let us take a step back and see how we can obtain the address of a call or jump ESP instruction. To find it, we can use the following command. We are instructing Mona to locate all the jump or call ESP instructions in the module's named kernel. Let us run it and see what we obtain. Notice that we can return to the log view by using the key shortcut Alt+L. Here we go. As we can see in the output, Mona tries to find all the call or jump ESP instructions in the following modules. At the end, we can see that there are 5 jump ESP instructions and 3 call ESP instructions. On the left, we can see the addresses of these instructions, while on the right, we can see some information about the module. Notice that in our environment, ASLR is enabled. Therefore, if we reboot the machine, these addresses will change. Let's be sure that the addresses are correct by double-clicking on one of them. This will open the CPU view. Here we are. We can see that at the current address, we have a jump ESP instruction. Let's go back to the log view and select one of the following addresses. In our example, we will copy the last one. Now, let's go back to our script and paste it. We have to append it to the junk bytes, but we also have to convert it in little endian. Therefore, we will type it in the reverse order. We're almost done. We just need to append our shellcode to our payload. For now, let's add some no operation code and debug the application to see what happens. Remember that when the program encounters a no operation instruction, it will simply continue with the next instruction. Let's restart the server and the client. As we can see, the application crashes again. If we inspect the latest instructions executed, we can see that we're in our shellcode. Therefore, whatever we add after these, no operations code will be executed. Moreover, as we can see on the stack, the shellcode has been copied exactly after the call ESP address. Let's go back to our script and finalize it. In this example, we want to execute the Windows Calculator application. You can find many different shellcodes online. The one we're going to use is the following. Let's copy and paste it in our script and run the FTP applications for the last time. If the shellcode is correct, we should see a calculator window appearing. Here we go. It worked. We've successfully exploited a buffer overflow vulnerability and forced the program to execute our code. Notice that the exploit works even if we do not debug the FTP client. Let's prove it by closing immunity and running the FTP client. Let us also run the server and then try to establish the connection. Here we go. After a couple of seconds, we can see that the application crashes and that the calculator appears. This concludes our video training lesson on exploiting buffer overflows. Thanks for joining us.